So yes, and now let's continue with our lecture on the solar path diagram. Okay. So I think I have explained everything on this solar path diagram. Okay, so let's try with some example so that we can understand more about this. Okay, assume that this example 3.6 is actually for Palomar. Okay, we can try on this. The date doesn't matter, we're just looking on the question. I mean that the year 2018 or 2021 doesn't matter, it won't affect the result. Okay, so for first question, what is the azimuth angle at 12 p.m. local time on 20th of April and 23 of August? Maybe you try first. You try to look on the graph here. You want to look at line 20 April and 23rd of August. Okay, so if I refer to this, April and August will be on line 3. Okay, so if line 3, then we come back to this graph, line 3, or almost a middle graph. So the question asks, what is the azimuth angle at 12 p.m. local time? Okay, so from here we know that we're talking about April first line. April is on line 3. Okay, and then we know that 12 p.m. local time is here. Let's see, 12H. Okay, and then I want to know at 12 p.m. what is the azimuth angle. So it means that you need to draw one line until azimuth angle. Okay, but you can see that which point is 12 p.m. There is a 2 point cut through the 12 p.m. line. Okay, left or right. Okay, because you can see that as I mentioned previously, one line represents 2 days. For line 3 represent 20 of April and 23 of August. Okay, so it means that you go, the sun moves to the north side and then you turn, come back to the south. Okay, so you will go through every location twice a year. But now, which point refer to April, which point refer to August? I know that the intersection point between line 3 and 12 p.m. is what I'm looking for. But now we have 2 dates, 20 of April and 23 of August. Okay, how to get it? Okay, first we try start from the end, maybe line 1 or line 7, because there's only one point. And do notice that each of the line have the direction. Let's see the direction of the graph here. Okay, they mention the direction. So maybe we'll start from line 7. Line 7 is 22nd of December. Okay, so after December should be the January. Okay, now we start from line 7, December. This point will be January. This point will be February, March. Okay, and then this side will be April. Okay, April, May, June, July, August. Okay, you see that? So I know that the point near to the middle should be the April. Okay, this one is APR. And this one is August. Is that okay? Because we start from bottom, December, January, February, March, April, and then June, May, April, May, June, July, August. And then go to September and repeat again. So we follow the direction of the arrow here. Okay? So now the question asks for the azimuth angle. So you have to draw a straight line downward and then read from the graph. What is the azimuth angle? Of course, my line is not straight. You can draw the better line. Huh? So you can read from here. Should be slightly negative lah, if I check from here. Okay. Okay, so I would say that the value should be for April, there should be around, this is 0, so this 30, 10. Okay, maybe -3 and -5, still okay. So it means that the azimuth angle at in April should be around -3 degree. Okay, and then on this the 3rd of August, it should be around -5 degree. Can you follow? Okay, I hope okay for everyone. Okay, let's look on the second one. What is the day length in hour on 22nd of December? Day length, 22nd of December. So first, we determine which line to use. So as the question asks for 22nd of December, so definitely is a line 7. Okay, so what is the day length? How I know the day length? So day length should be the duration from sunrise to sunset. And I know that sunrise should be this one. Okay, and then sunset should be this one. So it means that now we need to know the time. Then we only can know the duration. From the graph, it's only give us the altitude angle and azimuth angle. Okay, so how are we going to know the time at sunrise? Okay, so first, do you notice that this 8H over here? So this refers to the 8 a.m. in the morning local time. So this point is 8 a.m. Okay, so what do you think is the sunrise? You can see that if I draw the lines at 7H over here, it should be around here. If you estimate now, it should be around here. And then our sunrise is over here, not yet touching the 7H. So can I say that the sunrise is around maybe 7:30 a.m. local time? Okay, before, because it's definitely before 8 a.m. but after 7 a.m. I just know that it's between 7 to 8, but exact value I don't know. Okay, so I can estimate around 7:30. Same thing happened here. Okay, this point is 16H, so it's 4 p.m. And at the bottom, I think very close to it, this one is a 5 p.m. Can I say the sunset is 4:50 p.m.? Okay, so from here I can measure the daylight. Daylight equal to, so 4:50 should be yes, 4:50, that's correct. So 4:50 60 50 minus 7:30. Then we know the daylight. Okay. So the daylight is 9 hours and 20 minutes. Okay, can follow? So first we know sunrise and sunset time, and then we can calculate the daylight. But this everything in local time, we cannot know what is the local solar time because not given. You can see that graph give you three data: altitude angle, azimuth angle, and local time. The rest is not given. Okay, so here we get the daylight. Then the next one, when is the sunrise and sunset? This question asks for local solar time. Okay, in sunrise and sunset on 22nd of June. Okay, first question. Do you know the local, sorry, do you know the solar time on any point on the graph? Do you know when is the solar time at sunrise? Do you know when is the solar time at sunset? Or any other point that you know the solar time? Anyone want to answer this? Which point of the graph you know that there is definitely, you can identify the local solar time? The A. Yes, correct. Tiong Liu, definitely correct. Z equal to 0. As we know that solar noon is Z equal to 0. Okay, because sun height, altitude angle will change with time. We know that it will be maximum at solar noon. Okay, so middle line. This line, we draw one line down. This line represents solar noon, where azimuth angle equal to 0 and altitude angle is the maximum for that day. Okay, so now I want to measure how much difference between solar time and local time. I have to base on the 12 p.m. local solar time and the 12 p.m. local time. Okay, so you have to measure how much is the difference. Okay, so from the question, you cannot simply take one point to measure because the question asked on the particular date, 22nd of June. So we have to go to 22nd of June, line 1. Okay, 22nd of June is line 1. So we enlarge a bit. Yeah, can you see that? This point is the 12 p.m. local time. This point is 1 p.m. local time. Okay. Okay, write this way. 1 p.m. local time. So maybe I write something like this. Makes a table. This is solar noon. Okay, sunrise, sunset. And we have a local time, local solar time. Okay, so first, solar noon, I know that solar time is 12 p.m. Okay, and then local time. What time is the solar noon over here? Anyone? What is the time over here? 12 p.m., 1 p.m. So what is the time over here? I think very close to 12. 12:15. Is it okay? Yeah, 12:10. Okay, 12. Okay. That is, I think, quite close. 12:10. Okay, let's say we use 12:10. Okay, so I can say that the sunrise and sunset time is, sorry, it's not sunrise. Local time and local solar time is 10 minutes different. Okay, now we write down the time for sunrise and sunset for local time, because the local time we can read from here. Okay, so this line is sunrise. Maybe close to 5:10 a.m. Is it okay? Sunrise. Okay, and then sunset, I think very close to 7, so maybe 6:50. Sorry, I will put 18:50. Okay, so you can see that when solar noon, local time is 12:10, local solar time is 12. At sunrise, local time is 5:10, so local solar time should be 5. Okay, and then same thing for sunset. This one 18:50, so this one should be 18:40. So I would say that sunrise and sunset, sunrise should be at 5 a.m. local solar time, and sunset is at 6:40 p.m. local solar time. Okay. The only thing we can make the comparison is on the solar noon. But remember that, let's say now the difference between local time and local solar time is 10 minutes for 22nd of June. But you cannot apply this for the entire year. It will be different every day. You can see that if you go to line 2, then the difference will be much different. Even both on line 2, one is May, one is July, you can see they're different. Okay, they're so much different. You cannot simply change it. So for every line, we have to find the different every time. Cannot apply for others. Okay, so from here we can get the sunrise and sunset time in LST, local solar time. So move to the next one. When is the solar noon on 22nd of February in local time? Okay, maybe you check and then let me know. Solar noon, 22nd of February, local time. Share your answer in the chat box. 21st of February. So should be line 5 lah. 11:50 UQ. Okay, so I think the difficult part is which point is February? The point at the left or the point at the right? If you identify the point correctly, then it should be okay. Okay, so first we need to know the point. If according to the number at the side, at the legend of it, so December, January, so this point is February. Okay, so same thing for 13H, 1 p.m. This point should be February. Yes. So when is the solar noon in local time? You choose 11:50 wrong already because it's already after 12 p.m. Yes, 12:20. I think 12:20. Okay, quite close. Okay, here is 12 p.m. Here is 1 p.m. So solar noon, I think 12:20, quite reasonable. Okay, so based on this, we can identify correctly. But of course, first you need to know which point is actually the 21st of February. Okay. Okay. If no issue, then we can move to the next graph. This is Palermo, Italy. Okay. Palermo, Italy is located 38 degrees north. So as we know that the sun will move to 3.45 degrees to the north of equator and move down to 3.45 degrees to the south of equator. Okay, but this one, Palermo is located 38 degrees north. So it means that the sun always pass through the south of the Palermo. Okay, so you can see that sunrise is on the right, sunrise is east, sunset on the right. So this one is west. So we know that this direction is south. So the sunlight pass through the south for all the year, all year long. Okay, but let's take second round. This is in Kuala Lumpur. Kuala Lumpur located 2.6 degrees north, which means that the sun sometime will pass through the north of Kuala Lumpur, sometime the sun will pass through the south of Kuala Lumpur. So we cannot have the graph similar to this, but we have two, something like this. So you can see this is one, and this is another one. Okay, should be connected until here. Okay, so it means that some of the time the sun pass through the south, some of the time the sun pass through the north. So how to look that? So first we need to identify the direction. Okay, so based on the value on the azimuth angle, we can know the direction. When the azimuth angle is negative, it means that in the morning or before the sun. So the sun definitely on the east side in the morning and to the west side in the afternoon. So just look on the positive value or negative value on the azimuth angle. Okay, so this direction should be south, east, west, and south. And then in this direction should be north. Okay, west and east. It should be connected to here. Actually, it should be something like a cylinder. Okay, so this point A and this point B is actually the same point. Okay, A equal to B. Actually, it's the same point, but now we want to draw in 2D, so we have to draw it in this way. Okay, so same thing, east, and here should be west. So this direction is north. Okay, so it means that in line 4, 5, 6, 7, the sun passed through the south of Kuala Lumpur. For line 1, 2, 3, the sun passed through the north of Kuala Lumpur. This is first thing that we can see from here. Okay. And you can see that the value, the graph actually we're touching the alpha equal to 90. So it means that we should have the subsolar point in the year long. Okay, maybe twice a year. Okay, but Palermo, you can see Palermo with maximum value we have for altitude angle is only around 75. But Kuala Lumpur, we can get up to 90 degrees. And even minimum, we also get very high. I think line 7 is minimum. Okay, around 65 or 70. And do you notice that north and south? You can see that this point, this is minimum point on north. Okay, point X is minimum point on the north side, and let's say this point is Y. Y is minimum point on south. Okay, so which one's closer to the sun? Okay, you can see that Y is have the lesser value of altitude angle. So lower value of altitude angle refer to the is getting further away from sun. Okay, so let's say we draw out the curve of the Earth. Let's say this Earth, north, south, and this is equator line. And Malaysia is over here, Kuala Lumpur. Okay, and then this is a sun, the movement of the sun. Okay, so it means that the sun will be getting furthest away from the Kuala Lumpur when it go to the south, correct? Because Kuala Lumpur is located slightly north. Okay, so you will be more angled if you move to the south. So as we can see here, yes, it's match our explanation over here. Y is lesser than X. Okay, and then the line, all the lines remain the same. Okay, so another one, I move first. So stop me if anything you need further explanation. We move to the next one. This one is the Bangkok, Thailand. Bangkok, Thailand and Kuala Lumpur is quite close. So the altitude is 13.5. But what's the difference now? Same thing. This is the east. This is the west. Okay, so this one south, this one north. And you can see that there's less line on the north. There's only two lines, 1 and 2. And 3, 4, 5, 6, 7 is on the south. Okay, so when your location is getting north, there's more day the sun will pass through the south of Bangkok. Makes sense, lah? Okay. And then let's say I want to know when I have the subsolar point, alpha equal to 90 degrees. Okay, so when? Okay, so from here, I know that subsolar point is over here, this line, or this point, when in maximum. They should have the one point go from morning and go to the top, 90, and then go down. And when is the day? Of course, we are not able to identify exact date, but we can check from the line. You can see that line 2 is on the north, but line 3 is to the south already. So it means that there is one day between line 2 and line 3, you have the subsolar point, and alpha equal to 90. So line 2 and line 3, April to May, between 20 April to 22nd of May. So if I look from here, it should be closer to 3. Okay, and line 2 is quite far, and line 3 is closer to the 90 degree. Okay, so it means that closer to 93, can I say that it should be end of April? Okay. And second point, same thing. From between line 2 and line 3, 22nd of July to 23rd of August. But again, it's closer to line 3. So maybe I can say beginning of August. Okay, so this when it hit the top of the graph, which is 90 degrees. Okay, let's try this. I already answered for the last part. When is the Lahanan, this is subsolar point at Bangkok? Okay, I think similar to the first one, Palamo. Let's try this for the second one. You try first, I will give you answer later. Of April and 23rd of August. So it's line 3. Line 3 and then eligible angle at 12 p.m. local time. So 12 p.m. local time is over here. Okay, so at this point, so again, we have 2 points. We have to identify the point correctly. So December, January, February, March. So on the top should be April. Bottom should be April, August. Okay, so we draw along the line. So you get the eligible angle on April and August. This is agak-agak. So if you use rulers, get the closer answer. But the azimuth for August should be lower. Do you notice that the value for this jack is not actually linearly changed with time? Okay, you can see that start from maybe, okay, we look on line 3. It start from negative 100 plus 105, let's say. But you see 7 a.m. and 8 a.m. The value of azimuth angle, the change of azimuth angle is very less. Same thing for 8 a.m. to 9 a.m. to 10 a.m. All is very small change only on the azimuth angle. But when it start to go to near to 12 p.m. local time and 1 p.m. local time, see how much change within 1 hour from negative 65 drop to around positive 90 in 1 hour. Okay, so azimuth angle can change a lot in one hour, but it's not really a linear relationship. Okay, so the second value, what is the day length in hour at Bangkok on 22nd of December? Day length. So again, you have to find the sunrise and sunset on December, line 7. Okay, so 6:40 maybe, and sunset, I think already not yet touched, almost touched. So 5:50. Okay, 6:40 to 5:50. So you can calculate the day length. So 11 hour and 10 minute day length. Then move to the next one, number 3. When is the sunrise sunset at Bangkok on 22nd of June? 22nd of June is line 1. Okay, line 1. So sunrise is at this point. Okay, you can see that negative value should be sunrise. So I 6:10 a.m. maybe. Okay, and then sunset is on the other side. Sunset maybe 18, 50 or 40 lah. We just can guess lah, agak-agak lah. We just know that between 18 and 19, it is 6 p.m. or 7 p.m. And okay, can I continue? The next one should be when is the solar moon on 21st of February? 21st of February. 21st of February is line 5. Okay, line 5 is over here. So you want to find the local time. This is LSD 12. Then which line is the LSD? LD 12. Okay, LD 12 is over here, but you should ask for February. So December, January, February. February is over here. So this one is the local time 12. So this point is local time 30. So can I say that local time equal to maybe 12:30 p.m. when solar moon? Okay. This for Bangkok. And we still have a few lah, but I think will be similar lah. Okay lah, I think this you can learn at home. You can try. If any question that you cannot answer, then you can raise up during the next lecture. Or else I think everything seems good. To find the edging angle, to find the day length, to find the difference between local time and local solar time, and then the sub-solar point. Okay, I think should be okay. Huh? Okay, and this is for Adelaide, Australia. You can see that now it's different a bit. Left-hand side is positive value. So positive value is actually in the evening, west. This one, east. So north. So the sun passes through the north of the Adelaide or the year. Okay. Okay, other than that, we still have this is the 2D sun path diagram. We also have the 3D sun path diagram. This one's still 2D, but it's in the other form lah, something like angle. Okay, and we also have 3D, something like this, 3D sun path. But of course, 3D sun path is quite new. We can just refer to the internet. If or you want to draw on the paper, it will be very tricky. Okay, just look on this first. Determine the altitude and azimuth angle at 9 a.m. local time on 1st of February. You can see that the angle north 15, 13, 45, 16. Okay, and then 10, 20, 30, 40, 50, 60, 70, 80. Okay, so there's one straight line, one is a rotational line. And the angle outside is azimuth angle, and the straight line is the altitude angle. So this one is alpha, this one is z. So now you need to find on 1st of April. 1st of April. Where's 1st of April? Oh yeah, here. 1st of April. Okay. So secondly, 9 a.m. You notice that the time over here, 6, 7 at the bottom. The 6, 7, 8, 9. Okay. So this is the time for 9 a.m. in the morning, local time. So you have to find the intersection point. So 1st of April and 9 a.m. Okay, I think I find the correct point. Eh? Okay, now I find the correct point. Then next thing, I need to find the altitude and azimuth angle. So for altitude angle, I need to draw who? Here. Okay, so the altitude angle alpha is 30 degree. Can you see that? Don't just get a straight line. Eh? You get 60, not this way. So we have to get in curve. Okay. And then jack, same thing. We draw from middle point, pass through the point and go straight. Okay, so I can say that jack is around 62. Okay, but this is the what value? Should be negative in the morning. Okay, so you should have the negative 62 degree. But of course, in the actually azimuth angle, some of the book it will give you the angle in 360 degree. But in the book I refer to, we will use positive and negative, which are negative for the morning and positive for the afternoon. Okay. So you can see the line over here. This line is middle line. Okay. So this part all is a afternoon. Okay, or we call it jack is positive value lah. Okay, here is jack equal to negative value. This I mean that this is just okay. In the exam, this is our standard sum path diagram. We are focused on 2D sum path diagram, but this one is just to show you in case I don't know where you work at, maybe your company use different kind of sum path diagram. Okay, so you need to know both lah. Okay, maybe I show you one website. I think this one. Loading. Okay, so this is a sum path diagram also. Okay, and then this graph website very good. You even can choose the location. You can see that you can choose the latitude, longitude. You can set your own. Okay, you can set longitude. You can set the latitude, the date and time, the azimuth angle. This is a sunrise and sunset and day length. Okay, and you also can show you on different graph. This one is 3D lah. Okay, so at this particular time, this is the location of the sun. Okay, so it gives you the value of the azimuth angle and altitude angle. But if you want to change the type, I remember I can change now, but now I can't remember. So you even the animation on the sun moon. can't remember how to change. I remember that I can change. You can play around with this lah. I share the link in the chat box. Let's try to change it into 2D. I remember I can change to 2D, but I can't. Okay, never mind. You play at your own. Okay, so this is a 3D somehow diagram. So now we already advanced until this point. Okay, and then let me show you a good video about everything about the movement of the sun. Let's give it some time. I will present a YouTube video. Okay, it is definitely a very good video to explain everything about the sun.
Hey, Vsauce! Michael here. Do you have a best friend who is there for you 24/7, 365? Sorry, that's not really good enough. If your friend truly had your back, they would be there for you 24.000067365.2421891. Also, George Washington was born on February 22nd, 1732. At least, that's what we're told. However, his family Bible says he was born on February 11th, 1731/2. So, which is it, Mr. I cannot tell a lie? Oh, and don't even ask about 1752. In Russia, 1752 looked pretty normal, but check out what the British Empire was up to that year. Nothing really out of the ordinary, except Ember. The second was followed by the 14th. Were 11 days just deleted? Where'd they go? What happened then? It is time to question time and how the Earth moves. Reconciling both of these things has led to some pretty strange things. We all love time-lapse videos of the stars moving across the sky, but really, we are the ones who are moving, tumbling through the universe on a giant wet rock vehicle called Earth with a windshield called the sky. As viewed from above the North Pole, we spin counterclockwise. West chases east. I always remember this by thinking of the US as a weird mane-headed animal with Texas and Florida legs running forward. But we don't just spin. We also revolve around the sun on a plane tilted 23.4 degrees relative to our spin. It's kind of nauseating at this scale. But from this perspective, you can see that the sun rising and setting is just the Earth pointing you towards and then away from the sun. This motion causes your sunrise, your noon, the moment when the sun is highest in your sky, before your sunset. To more closely investigate this movement, let's talk about meridians. You are on one at this very moment. Your meridian is just a line from where you are right now, straight towards the North and South poles. It's a line of longitude, as opposed to the horizontal lines that lay flat when north or south is up that we call flatitude, or actually latitude. The sun is highest in the sky to you, your noon, when your meridian is pointed right at the sun. A cool thing happens at this moment. All shadows around you point directly towards one of Earth's poles, unless you're on the subsolar point. The subsolar point is the point on Earth's surface directly below the sun. It's always somewhere. You can check its current location online, links as always in the description. On the subsolar point, shadows fall straight down so they can easily disappear. Twice a year, the subsolar point crosses over Hawaii, the only place in the US where it hits land. And when it does, it is called Lahaina noon, meaning cruel sun. Straight vertical objects look unnatural during this brief time, like they don't belong, as if they were photoshopped in without regard for reality. In Honolulu, a sculpture by Isamu Noguchi called Skygate casts a twisted shadow all day, every day, except during Lahaina noon, when its shadow is a perfect circle. You may not live in a place where the sun ever appears directly overhead, but once every Earth rotation, the subsolar point falls somewhere on your meridian, making it noon for you. The technical name for this noon for you is local apparent solar noon. The clock on your wrist and the clock on your phone don't tell you your local apparent solar time, because long ago we realized that if every meridian had its own time, a person just a few kilometers away, seeing different shadows than you did, would disagree with you on what time it was. So towns adopted their own time. Now later on, this trick was standardized and time zones as we know them today came about. But that's not all we didn't like about shadow-based sundial time. To explore deeper, we have to begin by asking, what's a day? I mean, obviously it's just the time it takes the Earth to turn around once, right? But according to what? Everything else in space is moving in some way too. The universe doesn't include a convenient sheet of graph paper at absolute rest we can trace paths on. The best we can do on that front is to look at very, very far away stars. So far away, like distant features of the landscape out the window of a moving car, they barely move as Earth does. Now, to them, a meridian on Earth completes a trip around about once every 23.9 hours. This is called a sidereal day. Sidereal means pertaining to the stars. Even though the sidereal day seems pretty clear, it's not what our calendars and clocks are based on, because there's a nearer star whose position relative to us has a bigger effect on our lives: the sun. Looking down on the North Pole at Earth's counterclockwise spin, the Earth also moves counterclockwise around the sun. After a sidereal day, the Earth has moved a bit along its orbit, so some more rotation is required for the same meridian to point back towards the sun again. This longer definition of one rotation is what the modern calendar and clock is based on. It is called the solar day. But here's the thing. Exactly how long the Earth has to rotate to complete a solar day changes day to day. Our clocks are just based on the average amount of time this takes. So throughout the year, they fall ahead and behind the sun. This is a solograph, a picture of the sun's path across the sky every single day. If our clocks actually told us local apparent solar time, if you took a picture of the sky every day at noon, you should get a line of suns. But this is what really happens. Over the course of a year, it will appear as though your clock is running slow, and then fast, and then slow again, and then fast again. This problem was known since at least ancient times, even if its cause wasn't. In order to reconcile the two, the equation of time was constructed. In this sense, equation means to reconcile. The equation of time was applied to what a clock said in order to compute the real time, the solar time a sundial would show. Now, some fancy clocks, called equation clocks, were made that would do this for you, but eventually, we gave up. We gave up and just said, no, the real time isn't what the sun says, it's what our inventions say. Now, this transition was a big one. It was humanity growing up. It was like the first time you realize you're stronger than your parents. We realized our timepieces were more regular and turned our backs on the timepieces nature had. But what causes this disagreement in the first place? As it turns out, the answer revolves around revolving, the way the Earth revolves around the sun. If the equator faced the sun all the time and the Earth always orbited at the same speed, the subsolar point would just stay right there on the equator throughout the year, and the amount of extra time spent rotating the Earth needed to do to finish a solar day would always be the same. But those two things aren't the case. First of all, the Earth's orbit is slightly elliptical, so its speed varies throughout the year. When it's moving around the sun faster around the beginning of January, the amount of extra turning time needed to complete the solar day is longer than when it's further away from the sun and moving more slowly. There's more. Because the Earth is tilted, the subsolar point is dragged throughout the year in a circle around Earth that's not the equator, so it changes direction, moving northeast, then leveling out and going southeast, before leveling out and going northeast again. During times of the year when the subsolar point is being dragged by Earth's orbit mostly east, it gains against Earth's spin faster. More time is required for the day to finish. Now, by coincidence, we are alive at a time when both of these phenomena lengthen and shorten days at roughly the same time, so they add up, making September 18th almost a minute shorter than the longest day of the year, December 22nd. For Northern Hemispherians, December has the shortest periods of daylight, but the whole solar day, from sunrise to sunrise, is for everyone on Earth the longest of the year on December 22nd. People in the north just spend most of it in darkness. Earth's tilt, it doesn't just affect how long a day is, it also affects how long a year is. This is because the Earth's tilt is what causes the seasons. For the half of the Earth tilted towards the sun, the same amount of solar radiation is spread across less space than it is on the other half, so there's more heat energy laid down per area. This causes what we call summer and winter for the other half. The amount of time from one of these seasonal orientations of the Earth to its occurrence again is called a solar year, or a tropical year. It's a very useful way to define a year because it contains every single season exactly, since it's based on the...
Okay, class, I think now it's already 6 p.m. I will share the link in the chat box for everyone to continue, if you still wish to continue. Okay, so I think we have done the calculation, all the calculation for how the sun moves, where is the location of the sun. And starting from the next lecture, we will learn about the solar thermal collector and also the photovoltaic system. Okay, so that's all for solar. That will be the largest chapter. Okay, any other question before we dismiss? Okay, very strange. Thank you. Okay, so if no more question from your side, then that's all for today. Thank you. And yeah, for RE, tomorrow is public holiday, so we do not have tutorial. Okay, thank you.